Hello and welcome to our CSE438 project presentation on skin cancer diagnosis using deep convolutional networks. My name is Zabeen, and these are the rest of my group members.
Hello, I'm Fardin Bin Rahman, and now I'll be discussing the introduction part. Skin cancer is an invasive disease caused by the abnormal growth of melanocyte cells in the body, which tends to replicate and spread through the lymph nodes to destroy surrounding tissue. The damaged cells manifest themselves in the form of a mole in the outer layer of the skin. Across the world, skin cancer is accounted for over 1 million deaths every month and 300,000 more monthly cases in 2018. Melanoma is listed as the 19th most common disease with the highest death rate. Although it has been a tough journey coping with the high mortality rate, the recent developments in AI and image processing has led us to believe that the survival rate may very well increase over time. A skilled dermatologist must execute a step-by-step approach for diagnosis, which is rather expensive both in terms of time consumed and labor exerted. Yet the results of the diagnosis may vary depending upon the expertise of the dermatologist. And reportedly, the accuracy of properly diagnosing skin lesions is below 80%. Skin cancer is mainly divided into three categories: basal, squamous, and melanocyte. Our main contributions are using CNN to classify 7 distinct categories of diseases with high accuracy and creating a lightweight, user-friendly model for applications. Now let us go to related work. In early 1990, computer-aided diagnosis systems were developed to help dermatologists overcome the difficulties in skin cancer categorization. The first studies using dermoscopic images were limited to classifying benign and melanoma skin cancer lesions. Since then, several approaches for tackling this difficult issue has been published. Out of them, CNN have made great strides in existing problems and quickly became the preferred choice for skin cancer classification. Since CNNs require large datasets to become familiar with the problem, current literature primarily uses transfer learning, which is a technique where a model trained for a source task is partially recycled for a new target task to solve the large dataset problem. Previous studies of computational classification by dermoscopy are not only lacking in general capabilities but also unable to improve the accuracy of MCS skin cancer classification. Unfortunately, most of the research so far has not used large datasets. This is a basis for a deep learning model to work well. Unlike these studies, our proposed model performs much better on 7 classes of skin cancer. Now let us move on to research methodology. And first, we have to go through workflow. On workflow, first we have to collect the raw dataset. After that, we analyze the data accordingly. Next, we augment the data for reaching higher accuracy, and then we process the data so that we can train the data efficiently. Now it is time for training and testing, and lastly, we evaluate and discuss the future study. For dataset, we use the HAM 10000. It has 7 classes and number of images corresponding to the classes is shown in the slide. For exploratory data analysis, dataset is diverse. The first graph is about gender. Here, most of the people are either male or female. On the next graph is about where the cancer is, and as we can see, the graph is rightly skewed. And the last graph is about the age frequency, and the graph is unimodal.
Assalamu alaikum. I'm Azharul Islam. I'm going to talk about the research methodology. Firstly, we check the missing values in our dataset After finding the missing values, we replace them with mean values of that column or feature. We then resize the image to 28 into 28 pixels with 3-channel RGB. We augment our data by using factors such as rotation, white shift, height shift, shear, horizontal, and vertical pitch. We augment the data so that there are no imbalance in the dataset so that we can get better accuracy. The dataset is divided into 60 column 60 20 column 20 training, validation, and test datasets.
I'm Farhadul Islam. I'll be talking about the CNN architecture of our study. So our CNN model starts with a 3-channel picture with a resolution of 28 into 28 pixels from the dataset. We use 5 convolutional layers with 3 into 3 kernel size. Moreover, we utilize max pooling layers with a pool size of 2 into 2 to minimize the computational cost of the layers. Additionally, we utilize default strides of 1 into 1 for all convolutional layers. We choose ReLU as the activation function here since its gradient is not saturated, which significantly speeds the evolution of stochastic gradient descent as compared to other activation functions such as tanh or a sigmoid function. Here, max pooling layer and batch normalization layers comes after each convolutional layer as a block, creating a convolutional block. Eventually, we transform the values to a one-dimensional array and begin adding fully connected layers to the CNN. First with 2304 nodes, then 256 nodes, 128, 64 nodes, and finally 32 nodes. To avoid overfitting in the model, we utilize a 15% dropout after the final convolutional block and after the flattened layer. The linear activation function is used as a network classifier at the output layer. It is a simple straight line activation function in which our function proportionate to the weighted sum of neurons or input. Linear activation functions provide a wider range of activations, and a positive sloped line may enhance the activation level as the input rate increases. And finally comes the output dense layer with 7 nodes, each being a class or a label. Here we can see the hyperparameter table. We select the values according to the obtained results. We select these values because we get the best outcomes according to these values. Here we select the input size as 28 into 28 because it keeps the model lightweight and gives us good results. The dropout value is set to 15%. This helps us to reduce the overfitting of the model and gives us a smoother train versus validation curve. We set the batch size to 8, which gives our model a very good learning process, even though it's computationally costly. We set the epoch to 50, but it stops somewhere between 30 to 37 max, as we are using the callback function to early stop the training session. So this is our train versus validation graph. It represents how good our model fits to the data. Because of using the proposed model in such a way, and of course using dropout layers, our model learns very well, and of course the curve is very smooth, and the validation and train curves are very near to each other. This proves that our model fits to the data very well.
Hi, I'm Sarah, back again to discuss the experimental evaluation for our project. Here we've used 4 metrics of evaluation. First of all, we have accuracy. The accuracy is defined as a ratio of the model's correct predictions to the total number of predictions made. Then we have precision. Precision is used to determine a proportion of correct identifications. Precision is calculated by dividing the total number of true positive outcomes TP by the number of predicted positive outcomes, TP plus FE. Then we have recall. The recalls are used to figure out what percentage of true positives is appropriately detected. Recall is calculated by dividing the number of true positives TP by the total amount of data, TP plus FN. This is an important factor. Similarly, the F1 score is a popular metric for assessing the effectiveness of machine learning algorithms. It is calculated as the arithmetic mean of accuracy and recall. It has a value between 0 and 1. Number of occurrences properly identified by the learning models is reflected in the F1 score. On the right, we have the equations for all the evaluation metrics. Now we'll discuss the experimental evaluation of our project. After a rigorous research, we get the accuracy of 98.4%, a precision of 98.5%, and a recall of 98.4%, which outperforms all popular methods with high accuracy such as those by Chaturvedi et al. And Milton. We get 98.053% accuracy using the original dataset, which also outperforms all the methods mentioned in Ballerini et al.'s paper. Detailed classification report of the training and testing dataset can be seen in the cancer.org link as well as Abbas et al.'s paper respectively. Chaturvedi et al. Shows the confusion matrix of both training and testing dataset. The matrix shows how well the model performs in almost all of the classes of the dataset. Lastly, we compare between our model and other existing models. Now, first of all, we have the mobile net system proposed by Chaturvedi et al., which yields an accuracy of 83.1%, a precision of 89.0%, and recall 83.0%. Then we have Milton's method, which included inception ResNet v2 with an accuracy of 70%, PNAS net 5 large with an accuracy of 76%, SENet 154 with an accuracy of 74%, and inception v4 with an accuracy of 67%. Then we have Chaturvedi et al.'s paper, where the methods used included inception v3 with an accuracy of 91.56%, precision 89%, and recall 89% as well. Then there was the ResNet XT 101 method with 93.2% accuracy and 88% in both precision and recall. Then we have the inception ResNet v2 method, which yielded 93.2% accuracy and 87% in precision and 88% in recall. Then there's exception, which yielded 91.47% accuracy, 89% precision, and 88% recall. The last method they used was NASNet large, which yielded 91.11% accuracy, precision of 86%, and recall also 86%. However, in the end, we see that our proposed CNN, deep CNN method proves superior than all of them with an accuracy of 98.4%, a precision of 98.5%, and a recall of 98.4%.
Again, I am Azharul Islam. Now I am going to talk about the discussion part of our project. From our study, we find that our model performs well if we design the CNN model with 64 kernel size. Instead of a smaller value, the model reaches comparatively higher accuracy. The fully connected layers is built using a series of dense layers where the number of nodes is reduced by half. This increases our accuracy by 1 to 2%. Moreover, our model is not as heavy as models mentioned in the table 5. Our model only has 17,44,711 parameters, which can be considered as a lightweight CNN. This also helps in app or web implementations, as lightweight models requires less space and are faster to work with. Overall, we can conclude that our study contributes not only in performance but also in implementation. Now, for the conclusion part, the number of people diagnosed with skin cancer is increasing day by day. As addressing this as a global issue to the public has become urgent. Recent progress in the field of deep learning has enabled medical professionals to automate the diagnosis with higher accuracy. Our work has outperformed all the popular CNN models, making our model ready to use for computer-aided diagnosis. The future work may deal with interpretable diagnosis, which will help medical professionals with visuality as well. The highlighted region will tell what our proposed model has predicted and why it has predicted such outcomes. This issue will ensure lesser risks in medical practices. Moreover, uncertainty quantification can ensure more reliability while diagnosing the patients. Thank you.